Hello friends, welcome to this 27th video on complex analysis. In this video we will study about trigonometric functions of complex numbers. Trigonometric functions. Already we know that for a real number x we define sin x as, we have something like this. We have a right angle triangle, right, and if this is your x, then you define this height, that is perpendicular, divided by this hypotenuse as the sine of that angle. Now we would like to know what do we mean by sine of z, where z is a complex number, right? This is what we want to know. So what we are doing, we have this description of the sine function. Okay, we have a similar description of the sine function when x is real. We know that e raised to power ix, we have this Euler's formula, is equal to cos of x plus iota sine of x, and if I replace I with minus I, so I have e raised to power minus iota x is equal to cos of minus x, that is again cos of x, plus iota, this is minus sign here, sine of minus x, so this is equal to cos of x, because cos is an even function, so negative x does not make any difference, plus it will become minus, because sine is an odd function, so sine of minus x is minus sine of x, so minus sine of x, right? Now you can add these two equations 1 and 2. So what you will get adding, you will get e raised to power iota x plus e raised to power minus iota x is equal to 2 cos of x. So therefore you get cos of x is equal to e raised to power iota x plus e raised to power minus iota x divided by 2, right? Similarly, you can subtract these two equations. So when you subtract these two equations, you will get e raised to power iota x minus e raised to power minus iota x is equal to 2 iota sine of x. Therefore you have sine of x is equal to e raised to power iota x minus e raised to power minus iota x upon 2 iota. So these are the values of sin x and cos x when x is real. Okay, so we will use the similar analogy to define the value of the trigonometric functions when x is actually a complex number, that is, it is a z. So basically what we have sine of x, we have sine of x is equal to e raised to power iota x minus e raised to power minus iota x upon 2 iota, and we have cos of x as e raised to power iota x plus e raised to power minus iota x by 2 when x is real, right? We have just derived these things in the last slide. So now similarly for z, a complex number, we define, this is the definition of sin x, sine of z, as e raised to power iota z minus e raised to power minus iota z by 2 iota, and we define cos of z as e raised to power iota z plus e raised to power minus iota z upon 2. So we are moving on the similar analogy, right? So whatever we have in case of real numbers, we are generalizing that for the case of complex numbers, right? So this is the definition, and then similarly you can define your tan z as sin z upon cos z, then you can define your cot z as 1 upon tan z, and then you define your cosecant of z as 1 upon sine of z, and you can define your cot of z, secant of z as 1 upon cos of z. So these are all the trigonometric functions defined in case of C2. We are going from complex plane to complex plane. So now let us look at some of the similarities between the sine in case of real numbers and sine in case of complex numbers. So let us look at some of the similarities. Sine means trigonometric function in case of real numbers and trigonometric function in case of complex numbers. Let us look at some of the similarities. Right, so let us do that. So we have first thing, in case of real line, when we have trigonometric function from R to R, we have, this is the function where this is the case when we have trigonometric functions from C to C. Right here, the first thing we have this thing dy by dx of sine of x is cos of x. Right, you can derive this thing here, dy by dz of sine of z. What is this? This is dy by dz of sine of z is e raised to power iota z minus e raised to power minus iota z upon 2 iota. So what is this? This is iota e raised to power iota z plus iota e raised to power iota z by 2, which is equal to e raised to power, this is negative sign, e raised to power iota z plus e raised to power minus iota z by 2, and this is nothing but cos of z. Right, so we get that dy by dz of sine z is cos z. So the first result is matching. Right, so we have dy by dx of sine x as cos x, and similarly in case of complex plane we have dy by dz of sine z as cos z. You have to note one thing first before doing this. Note that sine z, this is entire function, and similarly cos z is entire function. Entire means it is analytic everywhere. Why? Because in the definition of sine z we are using only e raised to power iota z, okay, and that too in the numerator. So this is, and we know that e raised to power iota z is analytic everywhere, therefore sine z is analytic everywhere. Similarly cos z is analytic everywhere. Right, so these two functions are entire functions. Right, you have to note this thing that sine z and cos z are entire functions. Okay, but this is not true for tan z or cosecant z, because we have in the denominator something that we will look on later. Right, so this is the first similarity. Now let us look at the second similarity. You can similarly prove that in case of, obviously we have in case of real number dy by dx of cos of x as minus sine of x. You can actually prove this thing here. Right, you can prove that dy by dz of cos of z is actually minus sine of z. The proof is similar. You can do this. This is very simple. Right, you can further prove some identities. For example, we have sine is a periodic function with period 2 pi. We have third similarity. We know that sine of 2 pi x is 2 pi k plus x is equal to sine of x, where k is an integer. Similar thing we can prove here. Actually, we have sine of 2 pi k plus z, right, is equal to sine of z. How you can prove this? It is very simple. You just use the definition. 2 pi k plus z is equal to e raised to power iota 2 pi k plus z minus e raised to power minus iota 2 pi k plus z divided by 2 iota. Right, now what is this? This is e raised to power iota z into e raised to power iota 2 pi k, and that is 1. Similarly here into 1 minus, here we have e raised to power minus iota z into e raised to power minus iota 2 pi k, that is again 1 from the last video. So this is equal to sine of z. So we have proved that sine in case of complex numbers, when you treat it as a function from C to C, is a periodic function with period 2 pi. Similarly, you can prove many identities. Okay, I'll just write those identities here. You can prove that yourself. The first is cos of 2 pi k z plus z is cos of z. Right, it means that cos is periodic function with same period in case of, as in case of real functions. Then you have this thing that sine of minus of z is equal to sine of z with a negative sign. Okay, that is sine is an odd function. Then you have cos of minus of z is equal to cos of z, that is cos is an even function. Then you can actually prove that sine square plus cos square z is equal to 1, that is our favorite identity in case of real functions. Then we have sine of 2z is equal to 2 sine z cos z. Okay, and then you have cos of 2z is equal to cos square z minus sine square z. These are very easy to prove. You just put the value of sine z, cos z and sine of 2z. Then you have some formulas. You have this formula that sine of z1 plus minus z2 is equal to sine of z1 sine of z1 cos of z2 plus minus sine of z2 cos of z1. Then similarly you can have cos of z1 plus minus z2 is equal to cos of z1 cos of z2 minus plus sine of z1 sine of z2. So these are the things which you can prove easily, right? Okay, now let us prove one more thing. We can prove that sine of z is equal to 0. Sine of z is equal to 0 if and only if z is equal to k pi, where k is an integer. Okay, it means that you have this function sine z from complex plane to complex plane. This is your function sine z. Where are the roots of this function? Roots of the function are here: 0, then pi, then 2 pi, then 3 pi, and so on. And here minus pi, minus 2 pi, minus 3 pi, and so on. So it means that sine z is negative 0 only on the real axis and nowhere else. So how to prove this? So first let z is equal to k pi. Then you can see that what is sine of z? Sine of z is equal to e raised power iota z minus e raised power minus iota z upon 2i, right? For k pi you have sine of k pi is equal to e raised power iota k pi minus e raised power minus iota k pi upon 2 iota. Now what is this? This is minus 1 raised to power k, okay, minus again this is minus 1 raised to power k divided by 2 iota. So this is 0. Okay, so it means that whenever z is equal to k pi you have sine z is equal to 0, and conversely when you have sine z is equal to 0, it implies that e raised power iota z minus e raised power minus iota z is equal upon 2 pi is equal 2 iota is equal to 0. It implies e raised power iota z is equal to e raised power minus iota z. It implies e raised power 2 iota z is equal to 0. It implies that 2 iota z is equal to 2k pi iota. This is from our last video on exponential functions. From here you get that z is equal to k pi. So this is how you get all the roots of all the zeros of this sine z, right? Similarly you can find the zeros of cos z. You can actually do it yourself. I'll just write it down. Cos of z is equal to 0 if and only if z is equal to pi by 2 plus k pi, where k is an integer, right? So it means that when you treat cos z as a function from c to c, right? So where are the zeros of cos z located? Zeros of the cos z are here: pi by 2, 3 pi by 2, 5 pi by 2, minus pi by 2, minus 3 pi by 2 iota. Okay, so these are all the zeros of cos z. Okay, I'm sorry, not these are not on the imaginary axis, these are on the real axis. These zeros are on the real axis. So you have these zeros here: pi by 2, and then 3 pi by 2, and then 5 pi by 2, and so on. You can actually check. When you have z is equal to pi by 2, what is cos z? Cos of z is equal to e raised power iota z minus e plus e raised power minus iota z upon 2. So e raised power iota pi by 2 plus e raised power minus iota pi by 2 upon 2. What is this? This is cos of pi by 2 plus iota sine of pi by 2 plus this is cos of pi by 2 minus iota sine of pi by 2 divided by 2. So your these things will cancel, and what is this? This is 0, this is 0, so this is equal to 0. Okay, so it means that both cos x and sin z, cos z and sin z, they are having their zeros on the real line. Okay, when you are treating them as a function from c to c, right, their zeros are located on the real line, right? Okay, okay, so you can note one more thing. You can note that cosecant of z, okay, which is 1 upon sin z, this is not defined when z is equal to k pi, because we just saw that k pi is a root of sin z, 0 of sin z. Similarly it is not defined for not defined. Okay, and similarly we have secant of z, that is 1 upon cos of z, it is not defined for z is equal to pi by 2 plus k pi, right? Similarly you have this cot of z, this is first of all tan of z, this is sine of z upon cos of z. This is again not defined for z is equal to pi by 2 plus k pi. Then you have cot of z, that is cos of z upon sine of z. Sine of z is in the denominator, it is not defined for z is equal to k pi. And you can similarly note these things. And more things which you can prove, we have dy by dx of tan of x is equal to secant square x in case of real functions, right? And similarly here also we have dy by dz of tan of z is equal to secant square of z. You can actually prove this. Similarly we have dy by dz of secant of z as secant of z into tan of z. Then we have dy by dz of cot of z is equal to minus cosecant square of z. And similarly we have dy by dz of cosecant of z is equal to minus cosecant of z into cot of z. So these are all the similarities between the trigonometric functions when we are in the from real to real line, and the trigonometric functions when we are from complex to complex plane. So one more thing which you should note, we know that in case of functions from R to R, when you treat trigonometric functions from R to R, sin x and cos x are bounded functions. These are bounded functions, but when you treat them as a function from C to C, sin z and cos z, they are not bounded function. They are not bounded functions, right? You can actually see, for example, if my z is equal to iota y, that is a purely imaginary number, what is cos of z? Cos of z is equal to e raised to power iota z minus plus e raised to power minus iota z upon 2, right? So cos of iota y will be e raised to power minus y plus e raised to power y upon 2. Its modulus, you can see that it can take any value. This is always positive, this is always positive, so you have sum of two positive numbers, and this number can grow as large as it wants, right? So this is an unbounded function. So this is a major difference between the trigonometric functions when you treat them as a function from R to R, and when you treat them as a function from C to C. That is in case when the functions are treated from R to R, they are actually bounded functions, and they are not bounded functions when you treat them as a function from C to C. So the last thing which I want to mention is, we have this thing, we define something called hyperbolic functions, right? What are hyperbolic functions? We define them like this. We define sine hyperbolic of z as e raised to power z minus e raised to power minus z upon 2, and we define cos hyperbolic of z as e raised to power z plus e raised to power minus z upon 2. And then we can use these things to define your tan hyperbolic of z as sine hyperbolic of z upon cos hyperbolic z. Then we have cosecant hyperbolic of z as 1 upon sine hyperbolic of z. Then we have secant hyperbolic of z as 1 upon cos hyperbolic of z. Then we have cot hyperbolic of z as cos hyperbolic of z upon sine hyperbolic of z, right? You can prove some of the properties. You can prove that dy by dz of sine hyperbolic of z is actually cos hyperbolic of z, and dy by dz of cos hyperbolic of z is equal to, you expect a negative sign but it is not there, it is actually sine hyperbolic of z. So there are not lots of similarities. Then you can prove this thing, that sine iota z is actually sine iota sine hyperbolic of z. This is the relation between trigonometric and hyperbolic functions. And then you have sine hyperbolic of iota z is equal to iota sine z. And then you have cos iota z is equal to cos hyperbolic z. And then you have cos hyperbolic iota z is equal to cos of z. So you can see that in case of sine, iota is coming out, and in case of cos, iota is not coming out. So what is this? This is the relation between trigonometric functions and relation between complex trigonometric functions and complex hyperbolic function. Complex trigonometric functions and complex hyperbolic functions, right? These are the relations we have. Now we can prove some more identities. You can prove, we have actually this thing, sine square z plus cos square z is equal to 1. we have this identity. You replace your z with iota z. What you will get? You will get sine square iota z plus cos square iota z is equal to 1. Now what is this? Sine iota z is iota sine hyperbolic z square plus cos hyperbolic z square is equal to 1. So it implies that we have cos hyperbolic square z minus sine hyperbolic square z is equal to 1, right? So similarly we can prove some more properties. So this video was about trigonometric functions and hyperbolic functions, right? So we are moving towards the main topics of the course, like Cauchy's theorem and integrals and so on, that we will be doing in the coming videos. Thank you.